Now we're going to look at a very different sort of method for finding eigenvalues, different from the transformation methods we've been looking at. This method is incredibly simple, but it only finds one eigenvalue at a time. The idea behind the power method is simply pick a starting vector v0 at random, start multiplying it by the matrix A, and eventually, unless you're extremely unlucky in your choice of starting vector, the vector will eventually turn into an eigenvector corresponding to the largest eigenvalue, the largest in absolute value. To prove that the power method works, we're going to assume that A is diagonalizable. The book continues to show that the method works even if A is not diagonalizable, but the proof is much more difficult. We're going to assume that A is diagonalizable, that is, that A is similar to a diagonal matrix D. Now we're not assuming that we know S and D, of course. If we knew S and D, we would have not only the eigenvalues but the eigenvectors of A already, because the eigenvalues of D are simply the diagonal entries, and they are the same as the eigenvalues of A, so you could just read off the eigenvalues off of D, and in fact the columns of S would contain the corresponding eigenvectors. So we're not assuming that we know S and D, we're just assuming that S and D exist. And in fact, if A is symmetric, or if all of the eigenvalues of A are distinct, you can prove that A is diagonalizable, and it's diagonalizable in a lot of other cases also, but not all matrices are diagonalizable. But we will assume that A is diagonalizable. We also, of course, assume that there is a largest eigenvalue. If we want to find the largest eigenvalue in absolute value, there has to be one, and we'll call it lambda 1. And you simply, if you take A to the nth power, it's a matrix multiplication, not commutative, but if you take A times itself n times, that's SD S inverse times SD S inverse, etc. And the s's cancel except for the first and last, and you have A to the nth power is S d to the nth power S inverse. And let's look at what d to the nth power looks like. The nth power of a diagonal matrix is simple. It's just you just raise the diagonal entries, which are the eigenvalues of A, to the nth power, and if you divide by lambda 1 to the n, which remember lambda 1 is assumed to be the largest eigenvalue in absolute value, you get the following diagonal matrix. And when n is very large, all of these diagonal entries are going to 0 except for the 1 or 1s corresponding to lambda 1, which are going to 1 or equal to 1. So the point is that d to the nth power over lambda 1 to the nth power converges to something, some non-zero matrix E. Normally E will just have a 1 in the upper left corner and 0 and all the other entries. If lambda 1 is a multiple eigenvalue, then you may have more than 1. The key thing is that this is converging to something, and that's where you need the fact that lambda 1 is that there is a largest eigenvalue. See, it doesn't hurt if a largest eigenvalue is multiple, but you don't want more than one different eigenvalue of the same absolute value. For example, if the largest eigenvalues are two complex conjugates, then lambda 2 over lambda 1 will not go to 0 or 1. It'll be oscillating. So under the assumption that there is a largest eigenvalue, d to the nth power over lambda 1 to the nth converges to something. And therefore, since a to the nth power is just s, d to the nth power s inverse, then a to the nth power or lambda 1 to the nth power is also converging to a fixed matrix we'll call G, which means that for large n, a to the nth power is essentially just some matrix G times lambda 1 to the nth. It's just a scalar multiple of G. The million and 1,000,001th power of A are just scalar multiples of G. So if you simply raise a to higher and higher powers. Eventually, each new power will be equal to the previous one times lambda 1. So that's one way you could find the largest eigenvalue, is simply raise a to a large power and then compare a to the n to a to the n minus 1. They're going to be scalar multiples of each other, and the scalar multiple will be lambda 1. We're actually going to, instead of raising a to the nth power, we're going to start with a vector v0 and keep multiplying it by a, so that vn, the nth iterate, will be simply a to the nth power times v0. The reason for bringing in a vector here is because if we take higher and higher powers of a, every iteration requires n cubed multiplications, matrix multiplication, whereas if we start with v0 and simply keep multiplying it by a, that's only order n square multiplications per iteration. And still vn plus 1 divided by, well, vn plus 1 will essentially be lambda 1 times vn. So if you take enough power iterations, each new vector vn plus 1 will essentially be lambda 1 times the previous vector. And since you can't actually divide vectors, we need to, well, you almost can, because vn plus 1 is essentially a scalar multiple of vn. But the way to find the ratio, which is going to be our lambda 1, one way of doing it, you could simply take ratios of the components. In general, we can take the dot product of vn plus 1 with some vector and vn with another vector, and that should approximately give us our lambda 1. That's the suggestion here. Basically, the idea is extremely simple. You start with an arbitrary vector v0, keep multiplying it by a every iteration, and eventually vn plus 1 is just a scalar multiple of vn. That multiple is lambda 1. So you're just comparing the two vectors, and here we do it by taking the dot product of each with some fixed vector u to get the ratio. Yeah, the only thing that can go wrong here, assuming there is a largest eigenvalue that is not tie for largest, is if the u dotted with g v0 happens to be 0, but if you pick v0 at random and u is some random non-zero vector, then, and g is definitely not the zero matrix, then the probability is 0% of that happening. You have to be extremely unlucky. We'll basically choose v0 using a random number generator to decrease the probability of that happening. But so extremely simple method. Notice that the rate of convergence depends on the ratio of the second largest eigenvalue to the largest, because the rate at which this d to the nth power over lambda 1 to the nth power matrix converges to E depends on the ratio of the second largest to the largest eigenvalue. Of course, if there are two different eigenvalues that are tied for largest in absolute value, such as plus and minus 10, then it won't converge at all, because you'll have a minus 1 to the n or something else of absolute value, complex number of absolute value 1 to the nth power, not converging to anything. So it makes sense that if it's a tie for largest eigenvalue, it won't converge at all. If it's nearly a tie, if lambda 2 is very close to lambda 1, the second largest is nearly as large as the largest, is going to converge slowly. So the speed of convergence, as seems reasonable, depends on how close the second largest eigenvalue is to the largest eigenvalue. Now, it looks like the power method can only be used to find the largest eigenvalue. But what if you want the smallest eigenvalue or another eigenvalue? Well, in this case, you simply apply the power method not to A, but to A minus pi inverse, where P is a number that the user chooses. In other words, you simply iterate Vn plus 1 will be A minus pi inverse times Vn, though we don't actually form the inverse. Inverses are anathema in numerical analysis, especially if A is sparse. You don't want to fool with an inverse. You simply solve this linear system every step. But in any case, the effect is the same as if you were simply applying the power method to A minus pi inverse. Now the eigenvalues of A minus pi inverse are simply 1 over lambda I minus p, where lambda I is an eigenvalue of A. So the power method applied to A minus pi inverse is, of course, going to find the largest eigenvalue of A minus pi inverse. What is the largest eigenvalue of A minus pi inverse? That's the one that has the smallest denominator. In other words, the one corresponding to the eigenvalue of A closest to p. And in fact, if you're willing to use complex arithmetic and choose p complex, you can even find complex eigenvalues this way. But you see, you're going to find the eigenvalue of A that's closest to p because you simply apply the power method to A minus pi inverse. You find that the largest eigenvalue of that matrix is 1 over lambda p minus p, where lambda p is the eigenvalue closest to p. And from that, once you know that, you can obviously solve for lambda sub p, namely, p plus the largest eigenvalue of A minus pi inverse. So this method allows us to find any eigenvalue of A, the one closest to p. If you choose p to be 0, you find the one smallest in absolute value. In theory, you can find all eigenvalues this way, though it's sort of like going fishing. You throw out a p and find the eigenvalue of A closest to p. Not the best way if you want to find all eigenvalues, but you can find any particular eigenvalue. As I said, you don't really want to fool with inverses here unless it's a 2x2 matrix and you're doing it by hand. For large A, especially sparse A, you don't want to form the inverse and multiply by that inverse every step. You simply resolve A minus pi Vn plus 1 equals Vn. However, since the matrix isn't changing every iteration, this is a good time to use the LU decomposition. In other words, the first shifted inverse power method iteration, as this is called, you solve it using Gaussian elimination, save the LU decomposition of A minus pi, and then all future iterations you use that LU decomposition and cut the amount of work tremendously. And that, remember, in that way you can take advantage of a sparse or banded A as well. Now, one obvious modification of this method that might be considered is suggested by the following. Remember that the rate of convergence of the power method depends on the ratio of the second largest eigenvalue to the largest. Well, the largest eigenvalue of A minus pi inverse is 1 over lambda p minus p. The second largest is 1 over lambda q minus p, where lambda q is the second closest eigenvalue to p. Therefore, the ratio of the second largest to largest is lambda p minus p over lambda q minus p, and that obviously is going to be decreased if you choose lambda p, or you choose p close to the eigenvalue you're trying to find. So in other words, the closer you choose p to the correct eigenvalue you're looking for, the faster this shifted inverse power method will converge. That suggests that maybe we should simply update our p every iteration. In other words, instead of choosing p to be fixed each iteration, we have a better and better estimate of the eigenvalue we're looking for. Why not update p every iteration? And in fact, that will cause it to converge a lot faster. There are a couple of disadvantages on the other hand. One is that now your matrix is changing every iteration, so you can't use the LU decomposition. And secondly, it's not guaranteed to converge to the eigenvalue closest to p. It probably will, but it's not guaranteed. So if it's important to find the eigenvalue closest to p rather than just any eigenvalue, then you might not want to use this. You might not want to update p every step. In the book, there's a Fortran and a MATLAB program to implement the inverse shifted power method. The user passes in number EIG, which is basically the P, the user choice of P, and the matrix, and a starting vector V0. However, if you input a starting vector of all zeros, which you normally should do, it will choose V at random, making the likelihood that bad choice of V will be used minimal. So this method implements the shifted inverse power method using complex arithmetic. In other words, EIG, which is we've been calling P, can be complex. If you choose a real P, then there's no hope of converging to complex eigenvalues, because complex eigenvalues of a real matrix always occur in complex conjugate pairs, and any real number is going to be equally distant from both of them, so you're never going to be able to converge to a complex eigenvalue unless you start with a complex P, which is allowed here, and then everything's done using complex arithmetic. Now notice there's a parameter called iUpdate. That's how often do you want to update your P. Now if you choose iUpdate equal to 1, P will be updated every iteration. As we mentioned, that means you're not absolutely guaranteed to converge to the eigenvalue closest to that P, and you can't use the LU decomposition. On the other hand, if you choose iUpdate large, then it won't ever update it. It'll use the normal shifted inverse power iteration. If you choose it to be 5, then it will, every 5th iteration, it will update P. As we said, the method is extremely simple. You start with a starting vector V0, and every iteration, if you're updating P, then you form A minus PI matrix, and you solve A minus PI times Vn plus 1 equals Vn. If you're not updating it, then you use the LU decomposition. These two routines are exactly the same as the Chapter 1 routines, DLINEQ and DRESLV, except that they allow complex arithmetic. And then after a number of iterations, Vn plus 1 should just be a multiple of the vector Vn. The way to find the multiple, we take the dot product with another vector. Remember, we suggested taking the dot product of both with some vector u. We actually take the dot product with Vn here, and the ratio of Rnum numerator to Rden is basically the ratio of Vn to Vn plus 1. And then we add P to that. That gives us an estimate of the eigenvalue of A closest to P. And we applied this routine to a 5x5 matrix that had one real eigenvalue and two pairs of complex conjugate eigenvalues. If we started with P equal to 10 plus 10i without updating, in other words, the normal shifted inverse power method, P equal to 10 plus 10i, it naturally converged to the complex eigenvalue closest to 10 plus 10i. Notice when we started with 13 plus 5i, it converged much faster because that's very close to the eigenvalue we're looking for, only 5 iterations instead of 25. We started with 7i, which, well, then it converged to this eigenvalue. When we started with P equal to 13, a real number 13, that's equally distant from the complex conjugate eigenvalues 13 plus or minus 5i. Therefore, it never converged. It oscillated back and forth because it finds the eigenvalue closest to p, and if p is real and the eigenvalues are complex conjugates, then there's going to be a tie for closest, and it won't know which one to converge to. Then we tried the same thing but updating every step, and it did converge a good bit faster as expected. In one more experiment, we set p equal to 13 plus 5i, which is very close to this complex eigenvalue, and you would expect it to converge rapidly to that eigenvalue. However, we played a trick on it. We input a starting vector which happened to be exactly equal to an eigenvector for the wrong eigenvalue. Namely, it was an eigenvector corresponding to the eigenvalue 4.879. Well, if you think about it, if you start out, if v0 is exactly an eigenvector corresponding to the wrong eigenvalue, what's going to happen every iteration? You're going to find that eigenvalue. If you set v0 exactly equal to an eigenvector corresponding to the wrong eigenvalue, and you did exact arithmetic, then obviously you're going to find the eigenvalue that corresponds to that eigenvector. And in fact, we did for a while, but then since we're not using exact arithmetic, that became unstable because this is not the eigenvalue closest to 13 plus 5i. This one is. So after a few iterations, it quit converging to the wrong eigenvalue and started converging to the right one, that is the one closest to p. So this is a case where numerical error actually has a good effect. So in fact, choosing the wrong starting vector is usually not fatal due to round-off error.